All right, so this first one, log of it. So this is how we're gonna. This is how we're gonna do these. We're just gonna say, well, what is this? What would I put in this box? Like, what should I? Some of you might already know, but what? Oh, it's frozen. What would I put in this box? Okay. And what we're gonna do, and I suppose if you like this technique on a test, you could do this off to the side to rebuild these properties, right? This is not, we're noticing something so that we have a property that we can use. This is not how you're going to solve things, but it is a useful technique to think about. So what I'm going to do is I'm going to rewrite this in exponential form, and it's a good question to always ask yourself. Again, hopefully you're getting more familiar with logarithms, but this question is saying the base, which is a, so that's like this a, okay? To what exponent, which is this red box, equals the other a, which is the argument of the log, which is that a. What do I put in the box to make it true? This one might seem a little bit strange because it's so trivial, but 1. So log base a of a is 1. That's the property. That's the result. Now we know that. An a can stand in for anything. It can stand in for another variable. It could stand in for an expression. The base of a logarithm can certainly be an expression. Log of base x plus 2 of x plus 2, right? Like that would be 1. So, or it could be a number, right? Remember, logarithms and negatives have a strange relationship, so not all numbers necessarily, but positive numbers, that sort of thing, it will work. Any questions about that? It's an easy one. Okay, what about the next one? So we're going to do the same thing. So a to some exponent equals 1. It's 0. If I wanted to solve this as an exponential equation, I again would go a to some exponent equals a to the 0. So I've rewritten 1 as a to the 0. Therefore, I've got to put 0 in here. But now we know that if the argument of a log of any base, the argument is 1, the result's going to be 0. Because remember, logs are asking, again, logarithms are very new. The notation is a bit strange, and it's a strange way. Like, a lot of people have a hard time turning their thinking around to get in the mindset of logarithms. Okay? But what a logarithm is saying is, what is the exponent on this that gives me this? What is the exponent? What is the exponent? So what is the exponent that's going to give you a result of 1? Well, it's going to be 0. Yeah. Sure. All right, let's keep going. So again, a to some exponent equals a to the x. Jason? It's going to be x. So this is like a more general version of the one directly above it, where we got 1. But it's worth pointing out the first one just because people forget that, oh, a means a to the 1, so it does have an exponent, so the result is 1. But really, this is the same thing, just instead of 1, it's an x. But we notice that it actually doesn't matter what the exponent is. The result is always just going to be the exponent. Now, this is really useful. This is like actually a big idea, and there's another version of this that we're going to notice something about a little bit later, and we're going to prove tomorrow that's related to this in some ways, that are really, really powerful ideas. And in fact, logarithms are interesting. If you click with this stuff, you're going to notice that when we get into some of the more interesting questions, there's like a ton of different ways you can solve them. They're just small little differences about almost the order of steps that you would do things, but it does change the way the question flows a little bit. There's a whole bunch of different ways because there's all these properties that you can rewrite things. And one of them is possibly by very often rewriting something like this. So you have the base and the base of the argument as the same, so log base a of a to some exponent, and then all of a sudden the logs are gone and I'm just left with the exponent. Like, that's useful, right? If I've got a log in the question and I want to get rid of it, this is maybe a useful property. So seems simple perhaps, but it can be very, very useful. Any questions? We're going to move on. This next one is, it doesn't come up naturally all that often, at least not in my experience, but it's one of those properties that's really, really easy. I would expect it to be on a test, maybe even on the final exam, that kind of thing. It's super easy to answer, but so many people leave it blank because they just go, what? I don't even understand what it's saying. But it's something we cover in class, and it's something that you should know. We're not going to rewrite it in exponential form because it's already in exponential form. So how about we rewrite it in logarithmic form? But this is going to be a little bit strange. It helps with the color coding things, but you can just watch for a minute if you want. So if I'm going to rewrite this in logarithmic form, remember, the base stays the same. So this power, the base is a. So I'm going to say log base a, and the argument and the result trade places, or in this case the exponent and the result trade places. So the red box moves there, and then log base a of x. So this is this exponent that's over here. Okay? So what do I put in the red box? X. Good. So this is just a property, a pattern that you want to notice, that it's very much like the one beside it, except written the other way around, whereas log base a of a to something, where a can be anything, but it's the same thing in both cases, obviously. So 3 and 3, or 10 and 10, or 18 and 18, or pi and pi, whatever it is, right? Log base a of a to the something will equal that something, or a to the log base a of something will also equal that something. They're kind of two different ways of writing the same thing, but notice that in both cases they just give you back that thing. People will be usually fine with this one and then forget this one because it doesn't come up as often and we're just not as used to it. Okay? It's in exponential form, so I can rewrite it in logarithmic form. This kind of rewriting, I used red boxes, but usually we would just use an X. I didn't use an X because there's already X's in them and it complicates things. It's just kind of a different way of thinking about it. But the red box was like a variable. And we're asking, what is this variable that will balance it, that will make it true? But we're solving by inspection. We weren't doing steps. We were just thinking about what would balance them, that kind of thing, right? So it's a neat little trick. It's a nice tool. But, again, we're just noticing, especially for those of you that came in a bit late, we're noticing things. This is not how you're doing the homework. These are 4 properties of the several that we're going to do today that now we should just know them and start to be able to use them. Okay? You don't have to do this every time. In fact, we're trying to learn to avoid rewriting in exponential form every single time. We don't want to have to do that. That's not how we always solve logarithms. We learn to solve logarithms as they are. Everybody good? Questions? All right. A different kind of property. This is one of the ones that we're going to do a proof of tomorrow. For today, we're just going to notice. What is something I could do with this to simplify? So inside the argument, 10 squared times 10 cubed is, how could I rewrite this? So it equals log of 10 to the 5. Good. Right? Add the exponents. And now we can use the properties that we just had, because something that is a reminder that we've talked about, but I know it's important to review a few times because people do forget, that when there's no base written in, we presume base 10. That is something you need to know. Your calculator does it that way, and so do we. This probably won't have an impact on you, but I've seen some software on computers that don't presume 10. They presume a different base, but for now, that's not something you need to worry about. Okay, so using the properties from above, what is this equal to? Look back at the properties if you have to, Megan. It's 5. Log base 10 of 10 to the something is the something. In this case, that something is 5, so it's 5. Very good? Are we okay with that? Not interesting? That was just like practice. That might be the kind of question that you have to solve in your homework today. So here's what I want to do. Well, let's just think about this for a minute. So I'm going to come over here beside it. And sometimes things in mathematics have these properties where if you're doing it to two things, there's some relationship where if you're doing it to each of them individually. You know what I mean? Kind of? Like distributive property? Okay. So is there any pattern here, log base 10 of 2 and log base 10 of 3? Right? Can I split those each separately into logs? We don't know this. We don't have a property that does this. We've never seen this before. We're exploring. But we're asking, is there something like distributive property? We wouldn't call it that necessarily, but something where we can, if I'm taking the log of two things together, can I somehow split it up and do it of them individually? So first of all, what is the log? The base of each of these on the right are 10 again. So the log of 10 squared, what does this evaluate to? 2. And what log of 10 cubed is going to be 3. And I know from what we did over here that this is going to equal 5. So here's where you have to really put on your thinking caps. Is there some operation that you know of that you could put in between the 2 and the 3 that would give us 5? I don't know. Think about that. We did this the other day where we thought about all the operations that we know. Why are you laughing? People are laughing. Anybody think of something? Nobody wants to put their hand up because it's too easy. Help me out here, somebody. Yeah, you can add them. So this is not a proof, but it turns out that it's true. We are going to do a formal proof of it tomorrow. It's called the Product Law of Logarithms. So if I'm multiplying the two things and they have the same base or not even the same base, but if I'm multiplying two things in the argument, I could add them separately, or vice versa. If I'm adding two logs, those logs have to have the same base. The arguments don't have to have anything similar, but they have to have the same base. Then I can write them as a single log. Again, think about all the things that we do algebraically with polynomials and rational expressions and trig expressions so far this year. Think of all the things. Being able to take two things and write them as one, think about how valuable that could be, or vice versa. Split them up in an important way, right? This can be really useful. Okay, so similarly for division, you can try this one on your own if you like. Yes? It's 10 to the 9 divided by 10 to the 6. So as you might expect, because of our familiarity with exponent laws, what's the relationship here that I can put in there? Yeah. And honestly, I mean, if you think about, think about the relationships, right? So I subtracted the 9 and the 6 up here to get 3. Well, if I do it separately, I'm going to get 9 here, and I'm going to get 6 here. I have to subtract, right? Because it's exponents and logarithms are really the same idea. We're doing the same thing. It's the same property, just written differently. And notation with logarithms is always different, so may not look the same, but it's the same idea. So I think when you look at it this way, it's fairly obvious that that should be true, and it is true. And again, these are properties that you're going to use here and there throughout your homework today and the rest of the unit. Solve some problems. Any questions? Everybody okay? So when you're multiplying, you add, you're subtracting, you divide. We'll do some questions with these properties as well. This is the last property that we're going to talk about, and I'll write it out for you after. We're just, again, going to play around with this a little bit. You might even want to just put your pencil down and watch. I'm not sure you have to write this down. You can if you want after. So again, I'm going to, and this is not what you're doing today. So you may ask the question, why is he doing that? Well, I'm doing it because I have advanced knowledge of how this is going to work out, and this is just to help us notice something, but ultimately you need to know the property that we're going to get out of it. Okay, and again, this is a really important property. So the thing we're about to do here is not a thing that you're going to do. It's familiar. We're just going to rewrite it in exponential form, but it's not something that you should know that that's what you would do in this case. So I'm going to write 2 to some x. There is no x, but if x was this, right? Remember, logs are asking what is the exponent. If I raise 2 to some exponent, that would give me 7 to the 4. Okay? And I'm going to do the same thing over here. And how about we use y for this one? So 2 to some exponent y is going to give me 7 to the 8. So here's the tricky part. This one's a little bit tricky. The other ones were obvious. I think this one's not quite as obvious, but the property itself isn't so bad. So even if some of this goes over your head, you'll be fine. You just have to know the property. If I was solving an exponential equation, and this is not a question that can be solved that way, but if it were, or if that's what we were trying to do, I'd have to rewrite 7 as a power of 2, right? So let's imagine that I did that. 2 to some exponent, I mean, there is an exponent, it wouldn't be a nice number, right? But there is some exponent you could raise 2 to get 7. It would be irrational, but you could do it. So 2 to the something, all to the 4, and 2 to the something, all to the 8. But that 2 to the something is the same in both cases. Okay? So this is like again, this is why, I don't know, if you write this down, it won't make much sense if you look at it after, but x equals something to the 4, where that's like 2 to the something, and something to the 8. So if I, again, that question mark is like 2 to the something, right? So this is where I can go, therefore, x equals 4 and y equals 8, right? Like I can get rid of the basis. And so what I'm just going to notice is that there's still going to be something in here. It's a different something, but it doesn't matter. Times that. What I'm noticing is, this is the important part of all this, this one's twice as big. Right? Because this is a 4, and this question mark is going to be the same in both cases. We don't care what it is. That's not the point of this. What I just noticed is this is twice as big. Because 8 is twice as big as 4, right? So whatever this one works, is that okay? Do people kind of get that? You might be asking, I sort of understand what he's saying now, but I don't really understand why. That's okay. Don't worry too much about it. You can take my word for it, honestly. Like I said, we're going to do a formal proof of this tomorrow, but for now you can take my word that we've done some shenanigans, and we got to the point where, okay, there's some question mark. I don't really know what it is, but for this purpose, we don't care. Same thing there. But what I do know is this one's going to be twice as big as that. And so when I look up at the top, what is twice as big in here? Like, twice as big means 2 times something, right? So what am I multiplying by up here that's making this? What I'm noticing is that log of base 2 of 7 to the 8, whatever it works out to, is twice as big as log base 2, 7 to the 4. I've doubled the exponent. In the argument, I double the whole thing. That's kind of what we noticed. And it's a little bit of a leap, but what I can do is I can say log base 2 of 7 to the 8 is equal to 2 times log base 2 of 7 to the 4. Right? Again, if you take my word for what we've done, kind of shows that that makes sense. And again, I don't want to spend too much time on this. We could look at it a little bit deeper, but I want to get to the result here. So we could kind of do this again and again. Like, doesn't that mean this would equal 2 times, or really 4 times, but 2 times log base 2 of 7 squared? Like, couldn't I keep pulling 2 out of the exponent out front? I mean, there's a relationship there. Does that kind of make some sense? So 2 times 2 is 4. I'm going to pull one more 2 out. So 2 times 2 is 4, times 4 is 8. So this is like 8 times log base 2 of 7 to the 1. So I pulled all the 2's out. And this is the property that's important here, folks. So if you kind of didn't follow all of that, it's okay. But take a look at the relationship between this line and the first line. When I have an exponent inside the argument of a logarithm, I could take that entire exponent out front instead and multiply it. It gives you the same thing. And we could actually think about this, and I would encourage you to do so in terms of like this property that we did, where you're multiplying exponents or you're adding them. So if I multiply a whole bunch, I'm adding a bunch of times, that's like multiplying out front. So there's all kinds of different ways you could look at it. We'll do a proof of it, but ultimately this is what you need to know. Okay, so therefore, log base x, of a to the r equals r times log base x of a. This is a super, super, super important property. Very, very useful. Again, it's kind of similar to the other ones that we were looking at, except they had the same base. If I go back up here, this was log base a of a to the x, so the bases were the same. This one's not quite that because it's log base x of a, but I can take that exponent on the a away from the argument in the log and multiply it out front. So this is the thing that you need to know out of all that. I'll never ask you to do anything like that. And we're going to prove it in a different way tomorrow. Any questions? All right, let's start using some of these and see how it actually works. Log base 5 of 10 plus log base 5 of 12.5. Log base 5 of 10. How many people think it's 2? It's not 2. That's not the relationship. It's not multiplying. The relationship is with exponents, so that's not going to work. What we were doing the other day was rewriting the argument. So in this case, 10. If you could rewrite 10 as a power of 5, you could solve that part on its own, right? But 10 is not 5 squared. That's a grade 9 mistake. Okay. So we can't solve log base 5 of 10. Not exactly. Those of you that can do it on your calculator, and there is another little formula that you can use that we'll talk about tomorrow, I think, even if your calculator doesn't do it, but you could get it. But it would be a nasty decimal, so it still wouldn't help all that much. What can we do? We can use one of those properties, which is log base 5. When I'm adding logs of the same base, I can multiply their arguments. 10 times 12.5. What's 10 times 12.5? 125. And if you are starting to click with logs, you probably know what the answer is and you could kind of just write it. Don't use your calculator. You're going to cheat yourself of the understanding by just using your calculator. You have to come to terms with this yourself. Again, on a test, we're going to ask you to do this without a calculator. So you could always rewrite the argument in terms of a power of 5. And then in this case, we can use one of those other properties, and it's just 3. Easy enough? So it was like 2 things that would have worked out to nasty decimals, but I used one of those properties, and I get a nice clean answer. Okay, so same thing. You can go ahead and do this one. What's the property when I'm subtracting? So it's 54 divided by 2. What's 54 divided by 2? 27. Log base 3 of 3 to the 3. So it's 3. So when we were exploring these, we were doing it kind of the opposite direction, right? Because I gave you this step, and then we went the other direction. But you can also start with this and simplify. In some cases, it makes it easier. Obviously, these questions are made up to work out nicely. So here's where we start to get into, there's all kinds of orders or slight differences in steps in how we could solve these problems. And I think everybody might do them a little bit differently. You got to practice enough where you kind of pick one that you like, okay? And it's the kind of thing where I imagine that in each student's head, they have a way that's like, well, this is obviously the easiest way to do it. Why would you do it any other way? This is the easiest way. But to somebody else, there's a different way that, for whatever reason, is easier. They just like that way better, right? So everybody's going to be a bit different. But in the end, you want to pick your way. And if to you, it's blatantly obvious that it's the easiest way, that's perfect. That's what you're aiming for. And that's just your way that you like to do it. So I'll do this a couple of ways to demonstrate. So first of all, I'm going to, whoops, I already did. I'm going to write log base 2. I'm going to rewrite this root, it's a cube root, as an exponent. And that's almost always a good kind of first step. In fact, let's do the same thing for both of these. And in this case on the left, I'm going to use that property that we were just doing shenanigans with, where I'm going to take the 1/3 out front. Because I don't like it to have like messy exponents in there, and I don't want to be like it's going to be too many exponents and stuff. So I like just taking it out in front and getting it out of the way, and I'll worry about it at the end of the question. And then how would I solve this? Log base 2 of 2 cubed, which is 1/3 times 3, which is 1. Right? Log base 2 of 2 to the 3 equals 3. That's one of our properties. I have my 1/3 out front. So it's very similar if I did it this way, but some people might like to leave the 1/3 as an exponent and just hammer away at the argument, always trying to put it in base 2. So if I do 2, rewrite 8 as a power of 2, it's 2 cubed. And now what property would I use when you're taking a power of a power? You multiply the exponents. So this is log base 2 of 2 to the 3. And see, no matter which order we do it, we end up basically doing the same thing. It's just a matter of where you do it. And so this is log base 2 of 2. 3 times 1/3 is 1, so that's 1. Same answer. You better get the same answer. One method, in my mind, is not better than the other, but it's a matter of the order that you see it. Yes? For now, I would. You don't have to show this step, that's for sure. You don't have to show that. You could jump straight to 1 there. But for now, I would absolutely show all the steps so you make sure that you are writing them out and getting them. And on a quiz, you'll have to show enough steps that you show you're thinking, that you're not just coming up with the answers. And even on a test, the final test, you'll have your calculator for it, or at least most of it. So then you'd be able to skip some steps, but we'd probably still ask you to show your thinking, right? So keep that in mind. Okay, let's do this one. Again, there's lots. I mean, there's like countless ways that you can start to split it up, and we won't do too many, but I might do at least a couple. How about we do it this way this time? What is 4 cubed? 64. What is 2 times 64? 128. So this is log base 2 of 2 times 64, which is log base 2 of 128, which is log base 2 of 2 to the 7. Is that right? Yep, that's right. Which is 7. I like expanded because I know my powers of 2 pretty well. 128, 256, 512, 1024, right? And I can find powers of 2 easily. But maybe somebody else doesn't feel that way and they wanted to do it a different way. Keep the number smaller. So another way you could do this is you could use the product law and get log base 2 of 2 plus log base 2 of 4 cubed, which is 1, plus 3 times log base 2 of 4, which is 2 squared, which is 1 plus 3 times 2, so 1 plus 6, which is 7. See what I mean? There's all these little different ways that you can solve these questions. It's a matter of the order. But in each case, we're using all those little properties, just rewriting things or putting things where you like them. The one on the right had a lot smaller numbers. But maybe it's a different, so it's easier to do in your head. I mean, 2 is easy to work with anyway, but I don't know. It's up to you to come to terms with the way that you like doing them. Any questions? Does anybody remember what the answer to this one is? You want to guess? What would you guess? This is that one where it's different because it's not a log, it's a power. It is 17, and you don't have to show any work for this one because we can't rewrite it. Like if you rewrote that in terms of logarithm, you'd need an x. So you'd have to say let x equal that thing, the whole thing, and then you'd have to put the x in. And so it's easier to just remember. And what I would do is I'd be like, oh, isn't that weird one that doesn't come up very often, but it'll probably be on the test. And you just look at the power, the base of the power, the base of the whole thing, which is 5, is the same as the base of the log, so it's just equal to 17. Okay? All right, let's keep going. I think these are just some more practice questions similar to ones that we did before. This is like a logarithmic equation, sort of, but it's a simple one because it's equal to x. It's very similar to the ones that we did before. So 3 to the x equals 243. And then we have to rewrite 243 as a power of 3. Does anybody know what it is or want to take a guess? How would you figure this out if it was a big number? And a question that always comes up every time we go through this course at this unit is, well, if we're not allowed to use a calculator, how big will the numbers get? Not too big, but that would be fair. 243 would be fair. Because you should know 81 is 3 to the 4. And then 81 times 3, like that's not too hard to do, or you kind of guess, well, so it's going to be 1 more than that, right? So it's 3 to the 5. And I wouldn't make a guarantee on how big the numbers will get, but we always make sure that they're fair. Like we think about that. Always make sure that they're fair. We know you don't have a calculator. Numbers will be fair. Okay, and in this one, I get 8 to the x equals 16. What do I do in this case where I can't turn 16 to a power of 8? Or not easily, at least. I mean, you can, but what do we do? Who remembers? Come on. Yeah, so I find something that I find some common base, right? And some people might think it's 4, but 8 would be hard to write as 4. So we'll go all the way to 2. So this is 2 cubed all to the x is equal to 2 to the 4th. And so 2 cubed all to the x is 3 times x. So therefore 3x equals 4 and x equals 4 over 3. Don't forget to go to the final step and figure out what x actually is. like this step, but also that step. Some people stop there because they're not used to going one further step. So make sure you go all the way. And one last thing that's kind of, I guess, tricky about this unit is there's a lot of different kinds of equations that you need to be able to solve. But, if you don't practice enough, they might all just kind of blend and look similar to you. And then if you're trying to use the wrong style at the wrong time, you're going to make mistakes. So that's really important to make sure that you've practiced enough that you kind of know what type of question each question is. So again, I'm going to rewrite both of these in terms of 2. So I'm going to write 4 in terms of 2, which is 2 squared, all the x. That's going to end up being 2 to the 2x. And how do I write 1/8? Well, I think about just the 8. And I know the 8 is 2 cubed. But if I want the 8 in the denominator, then I got to write it as 2 to the -3. Because that's going to flip it. But then it's still going to be 2 cubed, which evaluates to 8. People get a fraction result confused with a fraction exponent. We don't have an example of that yet, but up above we looked at a fractional exponent. So this is 2x equals -3 and x equals -3 over 2. So -1.5, but I never would have guessed that it would work out that way. This is the kind of question that if you have a fancy calculator, you would punch it in and it would give you the answer. Oh, it's -2.5 and or -1.5, and you'd write it down, but you'd get like 1 out of 3 marks for getting the answer because there was properties that you're supposed to be using and thinking that you're supposed to show to get to the answer. Okay. 25 to the x equals square root of 5 all cubed. So I'm going to end up, you may notice at this stage, you may not, probably most of you do, that you're going to end up writing them both in terms of 5. So this is going to be 5 squared, all the x. And this is, the square root of 5 can be written as 5 to the 1/2, all to the 3. And in both cases, I'm taking a power over power, so I multiply the exponent. So it's 2 times x equals 1/2 times 3, which is 3/2. Divide both sides by 2. It's just 3 over 4. Just different, slightly different kinds of questions with some negative exponents, some fractional exponents, different things like that. Okay, moving on. We still got more to do. I hope we're getting close to the end. We're running out of time here. Yes, we are. Almost done. I think this is the last kind of thing that we're going to look at today. Solve each of the following by taking the log of both sides. So this is a brand new skill. We only have 10 minutes, so I hope that's long enough for people to come to terms with it, but there's a chunk of the practice today that's on questions like this. I'm just going to change this for now from 300 to 1,000. Sorry if you already wrote it down. Which means you could probably solve this a different way, but we're going to do it the new way first. And if you want to go back and look at how you would do it a different way and see that they work out the same. So if I take the log of both sides, log and base 10, we don't need to write it. I'm going to write it this time of 10 to the 4x equals log base 10 of 1,000. So this on the left side here, log base 10 of 10 to some exponent, And so then this is going to be log base 10 of 10 cubed. So we get 4x equals 3 and x equals 3 over 4. Any questions on that so far? Okay, I want you to, for the next one, try to write the first line or two on your own by taking the log of both sides. It looks the same. Okay, and hopefully you got something like that. So you take the log of both sides. And the log base 10 of 10 is 1. So now I can do x minus 5 equals log of 50. Now the log of 50, here's where you're going to use your calculator. So if you don't have it out, you can pull it out quickly. But we can do that because everybody's calculator should at least do a log of base 10. So when we take the log of both sides, for now, we're using log base 10. Okay? And I'm going to add 5 to both sides. I'm going to get x equals log base 10. Remember, we're not writing it anymore, but that's what that means, of 50 plus 5. And I'm just going to punch it into my calculator and get a decimal and round to 1 decimal place if necessary. If your calculator is like mine and it opens a bracket automatically, make sure you close the bracket before you put the 5 in, or do 5 plus log of 50. And I got 6.7, 6.69897. You okay with that? So that kind of a question obviously would not be on a no calculator quiz, no calculator test, because you need a calculator to do the log part. Okay, a couple more. This one's a little bit different because it doesn't have the exponent's not written in, like it's not a base 10. Okay, but I'm going to do the same thing. I'm going to go log base 10 of 7 to the 2x equals log base 10 of 2500. So you see how this is taking the log of both sides. So I've taken the log of the whole left side and the log of the whole right side. You can't take the log of part of it separate from the log of another part. You got to take a log of the whole thing. On the left side, I can use this property. Both of these are base 10, so I can evaluate them with my calculator. I'm going to divide both sides by the log of 7. And then I'm going to divide both sides by 2. You could certainly do them both at the same time, but the 2 is just going to join the denominator. Like that. And you want to make sure that you know how to type this into your calculator properly. So if you have a chance, give this one a try. put brackets around the whole bottom if you need to, just to be sure. And I got 2.0 rounded to 1 decimal place. Any questions on that one? I think there's one more. Why don't you try this one while I'm getting the bracket ready? Again, we're just writing log, but remember it's base 10, base 10, base 10. Any questions? Timing. What does that one work out to?
We forgot.